Okay, so today or this week we'll be discussing about tree data structures. In the previous lectures, we have been discussing about linear data structures like arrays, linked list, stack, queues, etc. Here the elements are arranged in a linear fashion or it's a one-dimensional representation of data. So this week and the next week we'll be talking about trees and graphs, which are non-linear data structures which we use to represent hierarchical representation or relationship between elements. Here the elements, in the case of a tree, the elements are arranged in a nonlinear fashion or in a two-dimensional representation. For example, this given tree structure, you can see that there is some two-dimensional relationship between the elements. For making it simple to understand, let's take labeled uh, data. I think I'm audible, right?
Yes, sir.
Right. So here I have taken data which is alphabets from English language A, B, C, D, E, F, G, etc. So and arranged this in the form of a tree data structure. So coming to the definition of a tree data structure, it's a collection of nodes or vertices. So this represents a node A, B, C, D, etc. All these are nodes or we call it vertices. And the connection between these vertices A to B, B to E, etc. These are known as edges or branches. So A to B there is a relationship, A to C there is a relationship, A to D there is a relationship, D to H there is a relationship, and so on. So coming to the definition of a tree data structure, you can say that it's a collection of nodes or vertices and edges. It's a collection of nodes and edges. It's not only a collection of nodes and edges. There should be so there should be some relationship as well. Like for each of the node, you can see that for each of the vertex, you can see that there is an incoming edge. For example, M there is an incoming edge. For J there is one incoming edge. For F there is an incoming edge, etc. Only for this particular node A, there is no incoming edge. So yeah, from there itself, you can very well say the relationship between the number of edges and number of vertices in a tree. The number of edges should be strictly one less than the number of vertices in the case of a tree data structure. So if we have n vertices, you should have n minus 1 edges. So in this case, you have some number of vertices. Let's say it is n, then the number of edges should be n minus 1. Then in addition to that, the tree data structure need to have another property which comes inside the definition is if you remove a particular vertex, if you remove a particular node, for example, if you remove this node A and you remove all these edges A to B, A to C and A to D, then you can say that this part what is left behind will be a subtree, and what is left behind here it will be a subtree, what is left behind here will be a subtree. So if you remove a particular vertex and all the nodes sorry, all the edges that is coming out of that vertex, then what is left behind will be again a set of trees or subtrees. In the same, like if you remove this vertex, then you will get a subtree E, then another tree which is rooted at F, F, J, K, and M. So it's some sort of a recursive definition. You can say that there is uh, a tree is built from another set of subtrees. For example, a tree, this large tree is built from subtree 1, subtree 2, and subtree 3. A single node itself can be treated as a tree, and a node, a tree with, there can be a node with zero node, a tree with zero nodes as well. We will see all these things in the case of implementation. Before getting into the implementation or before getting into the details, let's discuss about some of the terminology, some of the terms which we are going to use in our discussion. Root of the tree. As we have seen, for all the nodes there is an incoming edge. For J there is an incoming edge. For F there is an incoming edge, and we have seen that the number of edges is one less than the number of nodes. So of course there is one node which does not have any incoming edge, so that is the root of the tree. In this case, A is the root of the tree. So A is the root of the tree. Then it's just the opposite convention of a natural view of a tree. In the case of a natural view, you can see that the root will come in the bottom portion, then the tree will be grown upwards. Here in the computer scientist view of a tree is just opposite, that is the root will be on the top, and you will be having all sort of branches, and at the end you will be having leaves. But in the case of a natural view, you will be having just opposite view. That is, root will be at the bottom, then you will be having branches upwards, and at the top portion you will be having leaves. The parent of a node, for example, let's take this node B. It has an incoming edge from A, so the parent of B is A. The parent of C is A. The parent of K is F, and so on. Child, child is just opposite. A has children B, C, and D. F has children J and K, and so on. So root of the tree, parent of the tree, child of the, sorry, parent of a node, child, children of a node. Then siblings. Siblings are children of the same parent. For example, E and F are siblings. G, H, I are siblings. B, C, and D are siblings. So, children of the same parent are siblings. Descendants. Descendants are the nodes which are accessible from a particular node. For example, the descendants of B are E, F, J, K, and M. These nodes are reachable from B. With one edge you can reach here, with 1, 2, 3 edge you can reach M, and so on. So the nodes which are reachable by using a path from the current node are known as the descendants of a node. For example, the descendants of A contains all the nodes. The descendants of B contains all the nodes what is uh, there below B. Ancestors of a node. For example, the ancestors of a node are node E are B and A. You take a path from E to the root of the tree, then the nodes which comes inside that path will be the ancestors. For example, the ancestor of M is J, F, B, and A. The ancestor of H is D and A. So, ancestor and descendants are just opposite concepts. Ancestor is you take a path from that node to its parent, then from its parent, and so on till you reach the root of the tree. So, that set contains the ancestors of a tree. The degree of a node, the number of edges that is coming out of that node is the degree of a node. For example, the degree of B is 2. The degree of D is 3. 1, 2, 3, 3 edges that is coming out of it. So degree of a node is the number of edges that is coming out of a node. Internal and external nodes. You can see that the degree of this node is 0. There is no edges that is coming out of this. The degree of this node is 0. For this node degree is 0. For this node degree is 0. For G, N, O, and I, for all these nodes the degree is 0. Those nodes which is the degree of the node is 0 is called the external nodes or leaf nodes. So they don't have any children. That sort of a node are called external nodes. All other nodes which are having a degree is called, which are having degree greater than 0 is known as internal nodes. So B, F, J, G, L, H, D, A are internal nodes. Levels are considered like this. This is the first level, this is the second level, third level, fourth level, and fifth level. So this tree has got level 1, level 2, level 3, level 4, and level 5. You can ask questions like how many nodes can be there in a particular level and so on. So this is level 1, this is level 2, this is level 3, and so on. So this node has 3 children. All those nodes will be at particular level. The children of all these nodes will be at some particular level. The children of these nodes will be at some particular level, and so on. So this is, the levels are counted by using the number of nodes. At this stage, you can say that there is only one node. If you take these nodes B, C, and D, to reach B, C, or D, you need to traverse through two nodes A, B, A, C, and A, D. So that is level equal to 2. To reach any node at this particular level, you can say that you need to traverse through three nodes A, B, and E, A, B, and F, A, D, G. So that is level equal to 3. The height of a tree or height of a node, I'll mark height this side. Height is equal to, here height is defined 1 less than the level, that is height is equal to 0 at this level. Height is counted by using the number of edges that you need to pass through to reach that particular height. This level height is equal to 1, this level height is equal to 2, and so on. So to reach this node, you need to pass through one edge. To reach this node, you need to pass through two edges. So the number of edges that you need to pass through to reach a particular node is called the height of the tree, or the height of the node, height of a particular node. So the height of this tree is 0, 1, 2, 3, and 4, and there are number of levels 5. Next is a forest. Forest is a collection of trees. For example, if you remove this particular node A, and if you remove this particular node A and all these edges, then you are left with one particular tree T1. T1. This has got only one node. This is tree T2, and this has got another set of nodes, which is T3. And you can see that all these trees having uh, disjoint sets of nodes in the actual tree. So these nodes are having some set of nodes. Sorry, this tree has some set of nodes. This tree is having some set of nodes, and all these nodes are disjoint. So this sort of a disjoint set of nodes and this sort of a collection of trees are known as a forest. So that's about tree terminology, different terms which we come across while discussing about tree data structure. Any questions so far? Okay. Next, we'll look at binary trees. So previously we have seen a general tree where we had something like we have seen that degree of a node. For this node we had degree is equal to 3. For this node we had degree is equal to 3, and so on. For a binary tree, it is very strict that you can have for a particular node you can have degree 0, 1, or 2. For example, for this node A you have degree 2, for B you have degree 2, for C you have degree 2, for these nodes D, E, F, and G you have degree 0. So you can have either degree 0 or degree 1 or degree 2. That is the only possible degrees in the case of a binary tree, and that's the term binary. And in the case of a binary tree, you are sure that you can have only maximum of two children for a particular node. So you can always name them like it's a left child of the node. A is having two children. B is the left child of the node A, and C is the right child of A. So you can always name it. So B is having a left child is equal to D, and a right child equal to E. So that sort of a tree is known as binary tree. Once again, binary tree can have only degrees 0, 1 or 2. In this particular tree, you don't have any nodes which is having degree 1, but you can have nodes which is having degree 1 as well. Yeah, for example, in this case, the second tree here, you have for this node you have degree equal to 2. For this node you have degrees equal to uh, degree is equal to 0. For this node you have a degree equal to 2. For this degree is equal to 3. So this is a binary tree, and this is also a binary tree. In this case you have a degree equal to 1, degree equal to 1, degree equal to 0. So this is also another binary tree. In this case you have degree equal to 1, degree equal to 1, degree equal to 0. So perfect, this is another possible binary tree. What about this? For this node, you have degree 0, degree 1, 2, and 3. For this node, you have degree 2, degree 2, degree 0. But in the this has degree 3, so this is not a binary tree. Just I was taking just a few examples. What about this? For A, you have degree 2. For C, you have this is just a rotated version of the same tree, right? Instead of writing the tree in this form, I have written it in some other in downwards and uh, right way, so that the links are or edges are shown in the right or down. So this is also another binary tree. So once again, a binary tree can have in a binary tree the number of the nodes can have degrees 0, 1 or 2. Number of binary trees. Let's see if we have if you're given with some number of nodes, how many different binary trees you can generate out of it. So we'll get into some of the formulas to identify what is the number of binary trees that you can generate with some number of nodes. That's this topic. First, we'll discuss about this sort of a representation, unlabeled nodes. Then we'll talk about something like labeled nodes. For example, if you have number of nodes is equal to 3, n equal to 3, then the possible number of binary trees are this. Sorry. So by using 3 nodes, you can generate a binary tree like this, another binary tree like this, another binary tree like this, another like this, that is the mirror image of this, then the mirror image of the first one. So for n is equal to 3, you can generate t3 equal to 5 number of binary trees, 5 different types of binary trees with the help of unlabeled nodes. With n is equal to 4, you can generate in the same way. With n is equal to 4, you can generate 14 number of different binary trees. So it will be like this. You have one more node here and one possible binary tree. Then another possible binary tree will be like this. Then another possible binary tree like this, and so on. If you take all this, if you count all this, and you can see that the total number of binary trees that you can generate with the help of 4 number of nodes is 14. This can be written as a formula like this: Tn is equal to 2n divided by n plus 1. This is known as Catalan number. By using that, you can say that n equal to 5, you can generate 42 number of different binary trees. 2n divided by n plus 1. So with n is equal to 0, you can generate only one binary tree. With n equal to 1 also, you can generate only one binary tree. With n equal to 2, you can generate two different binary trees like this. With n equal to 2, you can generate one binary tree like this. With n equal to 2, you can generate another binary tree like this also. As a left child of this, as a right child of this. With n equal to 3, you have already seen. With n equal to 4 also, you can say this. With n equal to 5, you can generate 42 number of binary trees. Then with n is equal to 6, how many binary trees? Once again, you can calculate this: 2ncn divided by n plus 1. This is another formula for Catalan number: sigma I equal to 1 to n t of I minus 1 into t of n minus I. You may calculate it by using this formula or this formula for 6, and you will get it as 132. For 6 number of nodes, you can generate 132 number of binary trees. This is generated like this: T0 into, for example, let's say you are trying to calculate it for n is equal to 6, then it will be T0 into T5 sorry, T0 into n minus I. Sorry, I equal to, from I equal to 1 to, this entry will not be there. So for I equal to 1 to n, so it is T1 t I minus 1, so it will be T0 t n minus I, so it is 6 minus 1, so it will be T0 into T5 plus then T1 into T4 plus T2 into T3 plus T3 into T2 plus T4 into T1 plus T5 into T0. So that sort of a summation you will get. This is another formula for the Catalan number, which comes out to be 2ncn by n plus 1. You can calculate it by using this formula also: 2ncn, 2 into n, 12, 12c6 divided by n plus 1, 6 plus 1, 7. 12c6 divided by, sorry, 6. 12c6 divided by 7. So this was a case of unlabeled nodes. Let's see what will happen if we have a label set of nodes. For example, you take this. This was with the help of unlabeled nodes for n equal to 3. Let's say you have labels here, then labels like A, then B and C. Then this itself can be written in different ways or multiple ways like this. It can be A, B and C, then it can be A, C and B, then it can be B, A, C. So this particular shape itself will be having six different number of uh, uh, choices, and this particular shape will be having another six number of choices. This will be having another six number of choices, which is comes out to be 3 factorial. So for label number of nodes, it will be 5 into 6. You have 5 different shapes, and each shape can take 6 number of different labelings. So it is 5 into 3 factorial. This is for n equal to 4, it is 14 into 4 factorial and so on. So the same formula you can apply Catalan number into n factorial for labeled nodes. Next, we'll look at height versus nodes. Some other formulas in the case of what is the height if you are given with some number of nodes. What is the number of nodes that is possible if you are given with some particular height, etc. For example, initially we'll look at you are given with the height of the tree is equal to 1. For height is equal to 1, you should have this minimum setup. Minimum number of nodes should be 2. Maximum number of nodes that is possible with height is equal to 1 is this particular setup, that is you can have maximum number of nodes n is equal to 3. For height is equal to 2, you can have you should have minimum number of nodes should be, your minimum number of nodes should be 3 and maximum number of nodes should be 7. If you have all the left and right child, then this particular setup will come, so maximum will be 7. If height is equal to 3, then minimum you should have n equal to 4, number of nodes should be 4, and maximum is 15. Maximum number of nodes, that is for all the nodes you should have all the left child and right child, then that sort of a setup will be having maximum number of nodes equal to 15. Any questions so far? Okay. So from this, we will try to find out the formula between height and number of nodes in a binary tree. For a minimum number of for what is the minimum number of nodes that is required for a particular height? What is the maximum number of nodes that is required for a particular height? From that pattern, which we have seen the case of three examples, the minimum number of nodes that is required for a given height h, you can say that n is equal to minimum number of nodes that is required to create a particular height h is h plus 1. That is for h is equal to 3, you should have minimum equal to 4. For h is equal to 2, you should have minimum equal to 3. And what about the maximum number of nodes? The maximum number of nodes, you can see that in this case at a particular level, this has one node, this has two, this has four, this has got 8 number of nodes. So at this level, it has got 2 raised to 0 number of elements. This level, it has 2 raised to 1 number of elements, because it has all the elements has got left and right child. So it comes out to be a geometric series like expression. So this is the sum of geometric series a plus ar square plus ar cube plus etc. There is some mistake in this. Sorry, forget about this. So it comes out to be 1 plus in the geometric progression series. You can take a as 1, this constant as 1, and r is equal to 2. Then this will be 2 raised to 0 plus 2 raised to 1 plus 2 raised to 2 plus etc. 2 raised to h. We have h is our h is the number of or maximum height. So it comes out to be 2 raised to h plus 1 minus 1. So it is in this case it is height is equal to 0, height is equal to 1, height is equal to 2, height is equal to 3. So here you want to sum 2 raised to 0 plus 2 raised to 1 plus 2 raised to 2 plus 2 raised to 3. So it will be 2 raised to h plus 1, 3 plus 1. So 2 raised to 4 minus 1. So it is 16 minus 1, the maximum number of nodes that is required to generate a binary tree of all the nodes is with height is equal to 3 is 15. So maximum number of nodes h is equal for a given height h is equal to 2 raised to h plus 1 minus 1. Now let's see the opposite case, that is you are given with, in the previous case you are given with the height of the tree. Now you are given with the number of nodes in the tree. You would like to find out what is the minimum height that you can generate with this number of nodes, and what is the maximum height that you can generate with this particular set of nodes. Let's say you have some number of nodes is equal to 3. Your number of nodes is 3. Then what is the minimum height that you can generate? Minimum height is this. For example, height is equal to 1, and the maximum height is with number of nodes 3 is 2. And what is the number of minimum and maximum height you can generate with number of nodes is equal to 7. So this is the minimum height you can generate with all. This comes out to be just opposite case. Just we have seen the case of height versus nodes. This is nodes versus height. So in there we were talking about the maximum number of nodes. Here with the maximum number of nodes you can generate the minimum height. That's it. So with 7 nodes you can generate minimum height is 2. With 7 nodes you can generate maximum height is 6. So from these two examples you can find out a pattern. So the maximum height can be generated by using n minus 1 number of nodes, that is by using a series of just like a one dimensional sort of representation. That is maximum height can be can be obtained by this formula, h is equal to n minus 1 number of nodes. And what about minimum height? Minimum height is directly related with maximum nodes. So you have seen from the previous example that maximum nodes with a particular height is 2 raised to h plus 1 minus 1, isn't it? So n is equal to 2 raised to h plus 1 minus 1. You take this side, that is minus 1 this side, so it will be n plus 1 equal to 2 raised to h plus 1. So what is h plus 1 here? h plus 1 equal to log to the base 2. You're taking this 2 raised to this side, so it will be log to the base 2. Sorry. Okay. So and h plus 1 is log to the base 2 n plus 1. So h is equal to, that is minimum height is log to the base 2 minus this minus 1. Log to the base 2 n plus 1 minus 1. So that is a formula with for minimum height with some number of nodes. The maximum height is with n number of nodes is n minus 1. Minimum height is log to the base 2 n plus 1 minus 1. So with that we have seen with some number of nodes what is the possible what is the possible maximum height and minimum height. With some particular height, what is the minimum number of nodes possible in a tree, and what is the maximum number of nodes possible in a binary tree. So this is just a summarization. If height is given, minimum nodes is this, maximum nodes is this. If number of nodes is given, minimum height is this and maximum height is this. So you can see that the height of a binary tree, it ranges from log to the base 2 n plus 1 to n minus 1. So it comes out to be order of log n, log n, sorry, order of log n to order of. So you can take it as a summarization. The height of a binary tree, it always ranges from order of log n to order of n. Order of n will be a linear sort of fashion, that is, you will be having a linear structure. Order of log n is all the case where all the nodes are present. So the height of the binary tree is it ranges from with some n number of nodes, it ranges from order of log n to order of n. Now let's quickly see some of the relationship between internal nodes versus external nodes in a binary tree. For example, in this binary tree, you can say that there are this node is having degree 2, this node is also having degree 2. So the nodes with degree 2 is 2, nodes with degree 1 is this node is degree 1, this node is degree 1, so two nodes are having degree 1, 1, 2 and 3. Degree 0 is 3, so three nodes are having degree 0. So it is 2 plus 2 plus 3, 4 plus 3, 7. 3 plus 4, 7. Yeah. So two nodes are having degree 2, two nodes are having degree 1, and three nodes are having degree 0. Let's take another example. In this case, I can see that three nodes are having degree 2. This particular node, this node, and this node having degree 2, and 1, 2, 3, 4, and 5. Five nodes are having degree 4, and 1, 2, 3, and 4. Four nodes are having degree 0. In this binary tree, only one node is having degree 2. 1, 2, 3, and 4. Four nodes are having degree 1, and one node 1 and 2. Two nodes are having degree 0. Can you find a pattern in this? Anybody? The relationship between internal nodes and external nodes. What is an internal node and what is an external node? The nodes with degree 2 and nodes with degree 1 are internal nodes, and nodes with the degree 0 is external nodes, right? So the pattern is degree 0 nodes, number of nodes with degree 0 is number of nodes with degree 2 plus 1. So this is always true for a binary tree. Nodes with degree 0 is degree, in this case it is 2, degree 2 is 1. We cannot set a relationship with degree 1. So degree 2 nodes with degree 0 is always 1 greater than nodes with degree 2. Now let's quickly discuss about strict or proper or complete binary trees. For example, in this case you have all the elements, all the nodes. So this is a strict binary tree. In this case, you have uh, nodes like this. Yeah, strict binary tree or complete binary tree will be having all the nodes. You can have either 0 or 2 degree. You cannot have a degree 1 for a strict or proper or complete binary tree. For this case, all the elements are having this, and this nodes are having degree 2, and all the leaf nodes are having degree 0. Here, this node is degree 2, this node is degree 2, 1, 2, and 3 degree 0. So this is also a strict binary tree. In this case, degree 2, then this is degree 0, degree 1. So this is not a proper or complete binary tree. In this case, there is one degree 1 node, so this is not a proper binary tree. or complete binary tree. In this case, this node is having degree 3, so this is not a binary tree at binary tree also. So a strict proper or complete binary tree is something like you can have degrees 0 or 2, not degree 1. So in a strict or complete binary tree, you can take this formula: minimum number of nodes that is possible with a height h is n is equal to 2h plus 1, and maximum number of nodes that is possible is n is equal to 2 raised to h plus 1 minus 1. This is same as our general binary tree, and minimum height is also same as general binary tree, log n plus 1 minus 1, but maximum height will be different, n minus 1 by 2. The relationship between internal nodes and external nodes in the case of a strict binary tree, since we don't have nodes with degree 1, this for this you have uh, degree 2 nodes is 3, degree 3 nodes is, sorry, degree 0 nodes is 4, 1, 2, and this is having 3 number of degree 0 nodes, 1, 2, 3, 4, 5, sorry, 4 and 5, 1, 2, 3, 4, 5, 6. So you have 3 internal nodes, 4 external nodes, 2 internal nodes, 3 external nodes, 5 internal nodes, and 6 external nodes. From this, the pattern is very clear. In the case of a strict binary tree, the the relationship between internal nodes and external nodes is external number of external nodes is internal nodes plus 1. E is equal to I plus 1. So with this, I okay, that's it for today. Any questions? Okay, thank you.